Good afternoon, dear students. Once again, we are going to solve the problems which are related to gravitation. Here, we are going to speak about the Newton's laws of gravitation and the principle of superposition. The formulas involved in this heading is F equals G m1 m2 divided by r square, which is Newton's law of gravitation. The force between two masses will be calculated using this expression F is equal to G m1 m2 by r square. And second one, mass of the planet or satellite can be calculated with this expression as m equals 4 pi square r cube divided by gt square. M equals 4 pi square r cube divided by gt square. This is another expression to calculate the mass of the planet or satellite. Then the principle of superposition, as you know, f1 vector equals f1 vector plus f2 vector plus f3 vector up to fn vector. Based on these formulas, we are going to list out some of the problems. First one, two particles each of mass m go around a circle of radius r under the action of mutual gravitational attraction. Find the speed of each particle. So, they are asking you to calculate the velocity of or the speed of each particle. Let us consider two masses which are going around a circle of radius r. This is the circle over which the two masses are kept separated by a distance which is equal to diameter. So, the distance of separation between the two masses is equal to 2r, the diameter of the circle. So, force can be calculated from the expression F is equal to G m1 m2 divided by r square. Since the masses are equal, I can take it as m into m. And distance of separation is 2r, r and r 2r. So, 2r the whole square, which is gm square divided by 4r square. As this force provides the necessary centripetal force for these masses to revolve around the circular path, we can write gm square by 4r square. This force provides the necessary centripetal force mv square divided by r, from which we can calculate the speed as v equals square root of gm by 4r. This is the result, and this result can be used to calculate the magnitudes even. If the values of the mass of the planets and the radius of the circular path is given, we can calculate the velocity from this formula. Second problem, the mean orbital radius of Earth around the Sun is 1.5 × 10⁸ km, which means the Earth is revolving around the Sun at a distance of 1.5 × 10⁸ km. They have given mean orbital radius. Calculate the mass of the Sun if G equals 6.67 × 10⁻11 Newton meter square kilogram power minus 2. Mass of the Sun can be calculated using the formula m equals 4 pi square r cube divided by gt square. On substituting the data as 4 into 3.14 the whole square into 1.5, actually r is given 10⁸ km. We must substitute all the data in terms of SI units. So we have to convert it in terms of meter. So 1.5 into 10⁻11 meter. So 1.5 × 10⁻11 the whole cube divided by 6.67 × 10⁻11 into time period must be in terms of seconds. 1 year is 365 days. Each day has 24 hours. Each hour has 60 minutes. Each minute has 60 seconds. So you are converting it into seconds. On substituting all these values and simplifying, you will get m equals 2.01 × 10⁻30 kilogram. Right? This is the mass of the Sun. Third one, a sphere of mass 40 kilogram is attracted by another sphere of mass 80 kilogram with a force equal to 1/4 of a milligram weight. Actually, we have to go on with the conversions here. 1/4 of the milligram weight, when their centers are 30 centimeter apart, calculate the value of G. If they ask you directly the value of G, we can write 6.67 × 10⁻11 Newton meter square kilogram power minus 2. They are asking you by giving you the data. Mass m1 is 80 kilogram, m2 is 40 kilogram, separation is 30 centimeter. Force is 1/4 of the milligram weight. Actually, 1/4 of milligram weight must be converted in terms of Newton. First, you convert this milligram weight in terms of kilogram weight. 10⁻³ gram. Milligram is 10⁻³ gram. In terms of kilogram, it is 10⁻�6 kilogram. So, 1/4 of 10⁻�6 kilogram weight. In terms of Newton, you must multiply it with 9.8. So, 10⁻�6 into 9.8 divided by 4 Newton. This will give you the force. Force is known, masses are known, distance of separation is known. We can calculate the value of G. G equals 10 power minus 6 into 9.8 into distance of separation is 30 centimeter in terms of meter, 30 into 10 power minus 2 square divided by 4 into 80 into 40. On simplification you will get 6.88 in 10 power minus 11 Newton meter square kilogram power minus 2. Actually, for this problem, we can directly go on with the result, direct result, because G is the universal gravitational constant, 6.67 in 10 power minus 11 Newton meter square kilogram power minus 2. But a value is given. On that basis, what is the exact value of G which we will obtain? That is what we have derived here. Now, fourth one. How far from the earth must a body be along a line towards the sun so that the sun's gravitational pull on it balances that of the earth? Distance between the sun and the earth's center is 1.5 in 10 power 10 kilometer. Mass of the sun is 3.24 in 10 power 5 times the mass of earth. You may understand the question very clearly. Earth is there at certain distance from the sun, whose centers are separated by 1.5 to 10 power 10 kilometer. If some object must be projected from the earth, it will move up to certain distance. It will reach a point where the gravitational pull produced by the mass of the earth will be balanced by the gravitational pull produced by the mass of the sun. At this particular point, we used to call it as neutral point. At this point, the mass escapes out of the influence of the gravitational pull of earth and enters into the gravitational pull of sun. Do you understand this? It escapes out of the gravitational pull of earth and it enters into the gravitational pull of sun. Actually, if you throw some object from earth, it will move upward. At this point, it will be going out of the gravitational pull. If sun is there at this point, then it will be attracting this mass towards it. So at this point, the gravitational pull of earth ends and the gravitational force of attraction of sun starts. So this is the point P. If the separation is R, I can consider the point P is at the distance x from the mass of the earth and the r minus x distance from the mass of the sun. In case of equilibrium, we can write G me m divided by x square is the force between the mass, let us say mass is at this point P, between the mass of the earth and the mass which has been projected from earth. So G me m divided by x square. This is equivalent to the force exerted by the sun on the same mass. The sun exerting the force on the same mass. But the separation is r minus x. So G ms m divided by r minus x the whole square. On simplification, r minus x the whole square by x square equals ms divided by me. They have given the condition that the mass of sun is 3.24 in 10 power 5 times the mass of the earth. So mass of sun is 3.24 in 10 power 5 times the mass of earth. So ms by m is 3.24 in 10 power 5. R minus x divided by x is simply square root of ms divided by me, which is 3.24 in 10 power 5. Approximately the square root value is 570. R minus x is 570x, R equals 571x, x equals R divided by 571. R is given, separation between the two centers, mass of the earth and mass of the sun. X equals 1.5 in 10 power 10 divided by 571, which will get 2.63 into 10 power 7 kilometer. So we can say the mass which has been projected from the earth we can consider will be, if it is said to be at a distance of 2.63 in 10 power 7 kilometer, then the force exerted by the earth and the force exerted by the sun will tend to balance each other. Right? This force, this is the force exerted by earth and this is the force exerted by sun. These two forces tend to balance each other. So this is the point where the mass of the object is said to be out of the influence of earth and is entering into the influence of sun. So we can say this is the equilibrium state. The forces are balancing each other, Fe and Fs. Right? Then, based on force, in 2017 a question was asked. Two astronauts are floating in gravitational free space after having lost contact with their spaceship. The two will. What will happen? Right? The two astronauts are floating in the gravitational free space after having lost contact with their spaceship. Out of a spaceship they are existing. in free space. So they are totally out of the control of spaceship. What will happen to astronauts? Astronaut A1, astronaut A2. These two people are in space. This is space. They are in space. So what will happen? They have definite masses, let us say M1 and M2. So they are separated by a distance R. So what will happen? M1 will attract M2, M2 will attract M1. So I can write F12 and F21. So that we can say here the two forces are acting towards each other. So they will move towards each other. They will move towards each other. What exactly we have to speak out is, they are said to be in a state of weightlessness. If they are going out of spaceship and they are floating in space, then they are out of the force of gravity, which means they are feeling weightlessness. But between themselves, any two bodies existing in space will experience a force of attraction, so that they will move towards each other, right? The next set of formulas what we are going to use is acceleration due to gravity on the surface of Earth, which is G equals gm by r square. Mass of Earth is m is equal to g r square divided by capital G. Mean density of the Earth is rho equals 3g by 4 pi capital G r. This is obtained from this expression. G equals g mass is density into volume 4 by 3 pi r cube divided by r square. This gets cancels out. So you will have 4 by 3 pi r rho g. This is the expression from which we can calculate rho equals 3g by 4 pi gr. And weight of the body, as you know, W equals mg. Examples related to these formulas. If the radius of the Earth shrinks by 2%, if the radius of the Earth shrinks by 2%, this is the radius of Earth. If it shrinks by 2%, this decreases by 2%. What will be the value of acceleration due to gravity if the mass remains constant? Mass of the Earth remains constant. Then what will happen to the value of g? Acceleration due to gravity on the Earth's surface is g equals gm by r square, as you know. Taking log on both sides, you will have log g is equal to log capital G plus log capital M. R square is there in the denominator, so minus of 2 log capital R. As g and m are constants, as you go on with the differentiation, this constants, differential of constant is 0. Log g, log x is dx by x. So dg divided by g equals minus of 2 into dr divided by r. dr by r, that is the radius of the Earth shrinks by 2%. This change in radius dr by r is 2%. As it is said to be shrinking, we are introducing a negative sign, minus of 2 divided by 100. So changing the value of acceleration due to gravity, dg divided by g equals minus of 2 into dr divided by r has been substituted as minus of 2 divided by 100. Percentage dg divided by g into 100% is equal to 4 divided by 100 into 100%, so you will get 4%. The value of acceleration due to gravity increases by 4%. If the Earth, whose radius shrinks by 2%, then the value of acceleration due to gravity increases by 4%. Right. This is the same procedure which we have to follow to calculate all other physical quantities. If they ask you what will happen to the value of mass keeping radius, actually they have given radius is shrinking. So we are deriving a formula like this. What will happen to the value of g if r remains constant if the mass decreases by 2%? Then correspondingly you can calculate the expression like this. Right? So value of g will also decrease by 2%. Right? A man can jump 1.5 meter high on the Earth. Calculate the approximate height he might be able to jump on a planet whose density is 1/4 of the Earth and whose radius is 1/3 of the Earth. They are comparing it with density and the radius. Acceleration due to gravity in terms of density is given by g equals 4 by 3 pi g r rho. This is the expression 4 by 3 pi g r rho. If it is on the planet, the value of density is rho prime and the value of radius is r prime. So the value of g prime can be given as 4 by 3 pi g r prime rho prime. Here r prime is r by 3 and rho prime is rho by 4. On substitution, you will have g prime equals 4 by 3 pi g r by 3 into rho by 4. So 1/4 of 4 by 3 pi g r rho. 4 by 3 pi g r is nothing but g, value of acceleration due to gravity on the earth. So g prime is 1/12 of g. Assuming that the man puts in the same energy in jumping high on the earth and on the planet, because question is this one: what must be the height of the man above the planet whose density is 1/4 of the earth and whose radius is 1/3 of the earth? If he jumps over the earth's surface, he is reaching a height of 1.5 meter. If he is jumping on some other planet whose density and radius varies, then what will be the height attained by him? So he is putting on the same energy to jump on from the same planet as well as from the earth. So mg prime h prime is the energy spent by the man in jumping above the planet. mgh is the energy that has been spent by the man in jumping above the earth. So on comparing these two, g prime is g by 12, h prime is to be calculated. So we can simply write h prime equals 12h. H is already given 1.5 meter, which is the height above the earth the man jumps. So h prime equals 18 meter. So this is the height to which the man jumps on off from the planet if its density and the radius changes. Then, based on this idea, g equals gm divided by r square, we have a neat question, neat 18. If the mass of the sun were 10 times smaller and the universal gravitational constant were 10 times larger in magnitude, which of the following is not correct? Which of the following is not correct? If you look at the question, they are speaking about the mass of the sun. But if you look at the options, the time period of the simple pendulum on earth would decrease. Walking on the ground would become more difficult. Raindrop will fall faster over the earth. G on the earth will not change. They are comparing everything related to earth. But in question, they have given the mass of the sun were 10 times smaller. Mass of the sun were 10 times smaller. You should not confuse yourself between mass of sun and mass of earth. If you are writing the expression g equals gm divided by r square, this m corresponds to mass of the earth, not the mass of the sun. Not the mass of the sun. And the universal gravitational constant were 10 times larger in magnitude, which of the following is constant. So if you look at the expression, the value of acceleration due to gravity depends upon the mass of the earth, not the mass of the sun. Right? Value of g on earth depends upon mass of the earth, not the mass of the sun. And also it depends upon the value of radius. They are not mentioning about radius here. And the value of g is 10 times larger. So we can simply write g is directly proportional to capital G. If capital G becomes 10 times larger, if I consider this as g prime proportional to capital G prime, if g becomes 10 times larger, then g prime will also become 10 times, right? 10 times that of g. So here in this case g is proportional to g. So g prime is equal to 10 times that of g. What happens here is that the value of acceleration due to gravity on earth increases by 10 times. Value of acceleration due to gravity on earth increases by 10 times. But in the fourth option it is given g on the earth will not change. So this option is wrong. This is the choice. Right? What about the other options? Time period of the simple pendulum on earth would decrease. Time period of simple pendulum is given by t equals 2 pi into root of L divided by g. Right? If the value of g increases, time period t decreases. So this is true. Walking on the ground would become more difficult. Why? You will be acted upon by force of gravity. Your weight will be acting downwards. If g increases, weight will also increase, so that moving forward will be difficult. So this is also correct. Raindrop will fall faster. As the acceleration due to gravity is more, it will be pulling it, right? So that its speed will increase. So all these three options, 1, 2, 3 are correct. Fourth option alone is wrong. So g on the earth will not change. Where we shall see about the problems related to variation of g with altitude. The formulas involved are very simple. Gh equals g into r square by r plus h the whole square when h is comparable to r. You should not use GH equals G into 1 minus of 2h by r for all cases. If h is very much less than r, if any object is very close to the surface of earth, then GH equals G into 1 minus of 2h by r is applicable. If the height h is comparable to r, comparable to radius, if h equals r, h equals 2r, h equals 3r, in such cases we have to go with this expression GH equals G into r square by r plus h the whole square. Then the decrease in the value of G at a height h is, it is G minus of GH, which is equal to 2GH divided by r from this expression. G minus GH equals 2GH by r. This gives you the decrease in value of G at a height h. Percentage decrease in the value of G at a height h is G minus of GH by G into 100%, which is equal to 2h by r into 100%. Loss in weight of the body at a height h. If the object is taken to a height h, what will happen to its weight? How much it will change? Which is given by the expression mg minus of mgh, which is equal to 2mgh divided by r. Based on this formula, we shall solve some problems here. At what height from the surface of earth will the value of G be reduced by 36% from the value at the surface? The value of r is 6400 km. Suppose at a height h, the value of G reduces by 36%. We can say this is the earth, radius of earth is RE. At some height h, the value of G reduces by 36%. 36% is decreasing. So what will be its value of G at this particular height? It will be 64%. 100 minus of 36%, 64%. So we can say at a height h, the value of G reduces by 36%. It will become 64% as that on the surface of earth. So GH is 64% of G. GH equals G into r square by r plus h the whole square, because we do not know the value of h here. The value of h is not known. So in this particular case, we have to take this formula, GH equals G into r square by r plus h the whole square. GH is 64% of G, so 64 by 100 G equals G into r square by r plus h the whole square. Cancelling and simplifying, we will get 4h equals r, h equals r by 4. R is 6400. So we will have 1600 km. So at the height of 1600 km, the value of acceleration due to gravity decreases by 36% and becomes 64% of the value of G at the surface. This is one way. Second one, find the percentage decrease in the weight of the body when taken to a height of 32 km above the surface of the earth. Radius of earth is 6400 km. What is the percentage decrease in the weight of the body? Percentage decrease in the weight of the body has been given by the expression loss in weight of the body is mg minus of mgh equals 2mgh by r. If this mg minus of mg suffix h divided by mg is taken, then 2h by r. This will give you the change in the weight of body at a height h, right? When you want to calculate the percentage decrease, multiply it with 100%. You will get 100%. So from this expression, we are bringing out mg minus of mgh divided by mg. Change in weight divided by original weight. Multiplied by 100% will give you the percentage change in the weight of the object. So mg minus of mgh divided by mg is equal to 2h divided by r. Height is given 32 km, r is given 6400 km. On substituting and simplifying, you will get 1%. So percentage change in the weight at a height of 32 km above the earth's surface is 1%. Now, next one. A mass of 0.5 kg is weighed on a balance at the top of the tower 20 meter high. A tower is considered. At the top of the tower, its weight, it is at a height of 20 meter high from the ground, 20 meter high from the ground. A mass of 0.5 kg is weighed. The mass is then suspended from the pan of the balance by a fine wire 20 meter long and is reweighed. Find the change in the weight. It is weighed at this particular height and then it is suspended by a fine wire and the same mass is weighed. The wire is 20 meter long. which means the mass is weighed at a height 20 meters above the Earth's surface and the same mass is weighed on the surface of Earth. That's the meaning, right? They are asking you to calculate the change in weight, as usual. At a height h less than, very much less than r, you will have g prime equals g into 1 minus of 2h by r, which is g minus of 2gh divided by r. G minus of g prime, change in the value of acceleration due to gravity, is 2gh divided by r. Change in the weight is mg minus of mg prime, which is equal to 2mgh divided by r. mg is 0.5 kilogram force. Actually, Newton, it is equivalent to Newton. mg equals 0.5 kilogram force. They are given 0.5 kilogram. You are taking it in terms of 0.5 kilogram force. H is 20 meter. R is 6,400 kilometer. In terms of meter, 6.4 10 power 6 meter. Change in weight can be calculated by substituting this data. You will have 3.125 10 power minus 6 kilogram force. Kilogram force is another unit for Newton. Right? Kilogram weight also is another unit for Newton. Then, next question, 12. A body hanging from a spring stretches it by 1 centimeter at the Earth's surface. How much will the same body stretch the spring at a place 1600 kilometers above the Earth's surface? On the surface of Earth, a body of mass m is attached to a spring. It is suspended by a spring. It stretches by, let us say, 1 centimeter. The extension is 1 centimeter. The same is taken to a height of 1600 kilometers above the Earth's surface, and from here the same experiment is performed. What is the extension produced? X prime is asked. X prime is asked. So at the Earth's surface, we can say the force mg balances the spring force kx. At a height h, mg prime, where the value of acceleration due to gravity will change at a height h. So it is mg prime. There the extension will also change. So kx prime. G prime by g equals x prime divided by x on dividing these two expressions. As you know, g prime by g is nothing but r square by r plus h the whole square. R is 6,400, r plus h is 8,000, because r is 6,400, h is 1,600 kilometer. On summing up, you will get 8,000 kilometer. So 6,400 by 8,000, the whole square equals 16 divided by 25. X prime is 16 by 25 into x. X is 1 centimeter. So 16 divided by 25, which is 0.64 centimeter. So as you take the spring and the mass system to a height 1600 kilometer above the surface of Earth, due to the decrease in the value of acceleration due to gravity, the extension produced will also decrease. It is 0.64 centimeter low. Variation of g with the depth. As you know, at a depth d, gh equals g into 1 minus of d divided by r. Another expression is that when d equals 2h, the value of acceleration due to gravity at the height h will be equal to the value of acceleration due to gravity at the depth d. If the value of acceleration due to gravity at a depth d and the height h are equal, then this condition will exist. D equals 2h, 2 into h. The depth inside the Earth will be equivalent to twice the height above the Earth's surface. If this condition is satisfied, then the value of g at the depth and the value of g at the height h will be equal. Based on that, we are going to solve the problems here. Find the percentage decrease in the weight of a body when taken 16 km below the surface of Earth. If a body is taken 16 km below the surface of Earth, what will be the percentage decrease in its weight? As you know, gh equals g into 1 minus of d divided by r. Gd equals g into 1 minus of 16 divided by 6,400. So g into 1 minus of 1 by 400. Gd equals 399 by 400 g. So g minus of gd. This is the change in the value of acceleration due to gravity, which is 1 divided by 400 g. How? We can write g minus of gd is g minus of 399 by 400 g. 400 minus 399 by 400 into g, 1 by 400 g. percentage decrease in weight multiplied by mass. M into G minus half M into GH divided by mg into 100%. This is equivalent to G minus half GD by G into 100%. G minus half GD by G is 1 by 400. See? Into 100%. So this is equal to 0.25%. So when you take an object 16 km below the surface of Earth, then the percentage decrease in the weight of the body will be 0.25%. Then, next question. Imagine a tunnel is dug along the diameter of the Earth. Show that the particle dropped from one end of the tunnel executes simple harmonic motion. First thing, you are asked to show whether the object executes a simple harmonic motion. Then, what is the time period of motion? If it executes simple harmonic motion, what will be its time period? The average density, Earth is assumed to be a sphere, so that its average density is 5520 kg meter power minus 3. And value of G is 6.67 10 power minus 11 Newton meter square kilogram power minus 2. Neglect all the damping forces. When the object is set to undergo an oscillation, there will be some damping forces taking place inside the tunnel that must be neglected. The acceleration due to gravity at a depth d below the surface is given by Gd equals G into 1 minus half d divided by r. Gd is G into r minus d divided by r. I am taking r minus d as y, some displacement. R minus d as y. So G and r are constants. Gd is proportional to y. What is Gd? Acceleration due to gravity at a depth d. What is y? Displacement of the object. So acceleration due to gravity is directly proportional to displacement, which means the mass executes simple harmonic motion. So first thing what they are asking is satisfied. Then, if it executes simple harmonic motion, what will be its time period? Time period is t equals 2 pi root of displacement by acceleration. Displacement is y, acceleration is Gd. Gd is G into y divided by r. On substituting Gd, you will have 2 pi into square root of r divided by G. G is 4 by 3 pi G r rho. On substituting the value of G and simplifying, you will get time period is equal to square root of 3 pi divided by 0. 3 pi divided by 0, the whole root. So T equals square root of 3 into 3.14 divided by 6.67 10 power minus 11 value of G. And average density is 5520. On simplifying this, you will get 5059.77 seconds. So this is the time period of oscillation of the mass which executes a simple harmonic motion. Then, based on this formulas, two NEET questions were asked. About one in NEET 2019. A body weighs 200 Newton on the surface of Earth. How much will it weigh halfway down the center of the Earth? On the surface of Earth, it is 200 Newton. Halfway down the Earth, which means RE by 2. At this particular distance, what will be its weight? What will be the value of acceleration due to gravity? What will be the acceleration due to gravity? From which we can calculate the weight also, right? G prime is equal to G into 1 minus half d divided by r. D is given r by 2. The distance d, depth d is given re by 2. So G prime equals G into 1 minus half r by 2 into r. G prime equals G divided by 2. The value of acceleration due to gravity on the surface is 200 Newton. So 200 by 2, which is 100 Newton. So this will be giving you the value of actually G prime equals G divided by 2, from which we can calculate the weight where mg prime is equal to mg divided by 2. Mg is 200. So mg prime is equal to 200 divided by 2, which is 100 Newton. Right? In terms of Newton. Then, in NEET 17, the acceleration due to gravity at a height 1 kilometer above the Earth is the same as at a depth d below the surface of Earth. Then what will be the value of d? At a height h 1 kilometer, value of acceleration due to gravity is some value. If the same value of acceleration due to gravity must be obtained at some depth d, what will be the value of d? We saw the condition there. If Gd must be equal to Gh, then R must be equal, D must be equal to 2H. See, the comparison is made. G into 1 minus of D by H equals G into 1 minus of 2H by R. On cancelling everything, D equals 2H. If H is 1 kilometer, D is 2 kilometers. Simple. So this is a simple idea, shortcut. through which we can bring out the result. Which one? If the value of acceleration due to gravity at the depth equals the value of acceleration due to gravity at the height, then d equals to h. That's all. Then, the variation of g with the rotation of earth. This is the next heading, next set of formula. The formula is at latitude lambda, g lambda is equal to g minus of r omega square cos square lambda. This is known. At the equator, lambda is 0, so g equals g minus of r omega square. At the poles, lambda equals 90, so gp equals g. gp minus g means value of g at the pole minus the value of g at the equator will be equal to r omega square. This one. Right? If I substitute for g as gp, gp minus of g equals r omega square. So, if they ask you to calculate the difference between the value of acceleration due to gravity at the pole with respect to equator, then you can directly go on with this expression if angular velocity is given. gp minus of g equals r omega square. Determine the speed with which the earth rotates on its axis so that the person on the equator will weigh 3/5 as much at present. If the earth is considered, this is the equator, this is moving with the angular velocity omega. With this angular velocity, the man is weighing some value, let us say mg. If the new weight must be equal to 3/5 of mg, then what should be the angular velocity with which this earth must rotate? This is the question. What should be the angular velocity with which the earth must rotate? So g equals g minus of r omega square. The value of acceleration due to gravity at the equator is given like this. mg equals m into g minus of mr omega square. mg at the equator, the weight is 3/5 of mg. So 3/5 of mg equals mg minus of mr omega square. 2/5 of mg means I am taking the difference here. 2/5 of mg equals mr omega square. Omega equals square root of 2 by 5 into g divided by r. Value of g is 9.8. Value of r is 6,400 kilometers. So in 10 power 3, I am changing it in terms of meter. On simplification, I will get 7.8 in 10 power minus 4 radian per second. With this angular velocity, if the earth rotates, then the man whose weight on the equator is 3/5 as much at present. Right? This is one way of solving the problem based on the value of g with rotation of earth.